So I'd like to welcome you to the 913th meeting of the Amateur Telescope Makers of Boston. And our agenda today, we're going to have a brief business meeting, and we're going to try to keep it really brief so we get as much time as Jennifer as we can. And our presentation is by Dr. Jennifer Burt, who will give a presentation on her experiences with TESS and discovering new worlds. So we're really excited about that. And before I forget, I wanted to thank Maria for providing refreshments tonight. So as you're imbibing after, please make sure you give her a hand and appreciate her effort because it's a lot of work. So with that, we'll move right forward to the meeting minutes by John Harrington.
These will be very quick, since one, I wasn't at the last meeting, and two, I want to thank Glenn Chappell for kindly taking the notes. Let's see, the previous meeting, President Tom McDonough called the meeting to order at 8:02. Secretary's report was not given since I wasn't here. Eileen presented the treasurer's report. Chris Elledge presented the membership report. Glenn Chappell presented the observing report. We'll also take notes. Steve Clarity presented the clubhouse report. Mirror making committee report was not given. Outreach committee report was deferred for reasons that become obvious in a minute. Eileen Myers asked for help with setup and breakdown at the upcoming picnic, which I heard was a big success. Old business, Al Takeda announced that the clubhouse wireless router had gone down, but was again working, and he assisted Bruce Berger and Jim Geddes in repairing it. There being no business, Tom then moved on to introduce the first guest speaker for the evening, who's our very own Julie Kaufman, whose talk is entitled My Eclipse Experience. And she detailed her adventures chasing eclipses in Peru, the Caribbean, Europe, Zambia and Zimbabwe, Turkey, Mongolia, China, the Cook Islands, Indonesia, and even exotic Oregon, where I was last year. Tom then introduced the second speaker of the evening, which was basically the outreach committee. It's a talk presented by Rich Nugent, the members of the committee, Laura Saylor, and Glenn Chappell. Glenn began with a PowerPoint show entitled The Complete Idiot's Guide to Hosting a Star Party. He discussed the do's and don'ts of preparing and running a public star party. Laura Saylor then discussed the need to get newbies involved in star parties by giving them proper training. And after announcing upcoming star parties, the committee discussed PopScope and library telescope loaner programs and suggested other avenues for astronomy outreach. Refreshments were provided by Tom McDonough, and the meeting adjourned at 9:50 p.m.
Thanks, John. You still have a job, don't worry.
Thank you.
And I kind of wanted to highlight it's a lot of work to get the refreshments going because I did it last month, so special thanks to Maria again. So now we have the observing committee report, and I'll start off with this. Glenn couldn't make it today, he had some car trouble. He's fine, but car trouble, so I'll try to do my best to cover this. So as everyone is familiar, we're taking on the LVAS Observers Challenge. And the object of the month is NGC 7129. And it's a great object, so really challenging. And everyone's aware that Roger Ivester was running this program, and he's deferring to the Las Vegas, but still very much involved in putting together this report. So if you do observe this, send it to Roger, and we're a big contributor as a club to his observing list. So it's pretty exciting, and all the details are right here on it. And so go out and look at it. As you see, Glenn put together an observer's chart, and I'll probably butcher this, but this object's in Cephas, and there's a really nice picture. I don't know what it's attributed to, but I'm sure it looks just like that as you look through the IDs. at least with Mario's scope. And then I'd like to call up Rich for the next.
So I just wanted to offer up my own little observing challenge to the club. I don't know if you've noticed, but Venus has sort of left the evening scene. As of today, it was 22 degrees away from the sun, but because of the way the ecliptic hugs the horizon in the fall in the northern hemisphere, Venus this afternoon at sunset was only like a shade under 2 degrees in altitude. So Venus appears to have disappeared from the evening sky. The best time to look at Venus, of course, is during the daytime. Or you can wait for maybe a month to go by and catch it in the early morning hours. But observing Venus in the daytime is actually a lot of fun. If you have a go-to telescope, easy peasy. If you've got setting circles, that is also a nice, easy way to do it. I usually offset from the sun at that point. If you have an alt-azimuth like a Dobsonian, like I do, I kind of live in the alt-azimuth world now. I use my iPhone to give me the altitude and the azimuth and just move the telescope until I'm there. And with a pre-focused eyepiece, you should be able to see it. Venus is still incredibly bright. It's a nice crescent. And as it approaches inferior conjunction, that crescent will grow thinner, but also larger as it approaches the Earth. And remember, at inferior conjunction, you're looking at the nighttime side of the planet. The extreme of that is when you have a transit. And you look at the entire night side of the planet. But this year, on October 26th, Venus is going to reach inferior conjunction. Now, these inferior conjunctions, or any phase for Venus, subsequent repeats, are about 19 months apart. So it's been 19 months since we've had an inferior conjunction. This one is particularly favorable for daytime observing because Venus will be a little over 6 degrees away from the sun. Now that's 12 solar diameters, right? And you can observe it if you're very, very careful. Because you're going to be using an unfiltered telescope to look at Venus during the daytime sky. And if you're brave and you're very, very, very careful, Venus is going to present itself. You can't even see it here because it's so thin. I don't know if I should dare shut the lights out. Where's Glenn when we need him, right? You may not still be able to see it. It's invisible. It's maybe on the monitors upstairs you can see it, but Venus will be at inferior conjunction, 0.6% illuminated. It'll present itself as a little over, a smidge over 1 arc minute. But the razor thin crescent is something that is amazing to behold. So I would offer it as an advanced challenge. If you've never done it before, I would give it a shot. You know, you just have to be careful because think about where you're playing with your telescope. 6 degrees, it's hardly sport. I mean, I've actually looked at Venus in inferior conjunctions which are considerably closer to the sun, so close that I've had sunlight actually touching the mirror of the telescope off axis. You know, really close. I tend not to stray within 3 degrees of the sun, but I've been pretty close before, and it's actually pretty cool to look at. So anyway, I just wanted to offer that as an observing challenge, but you just have to promise me you'll be very, very careful if you give it a try. Call me or email me. I'll give you my tips. Anyway, yes, sir.
One of the tips is for photographing the crescent is to use a near-infrared filter like 0.9 microns. It'll greatly increase the contrast if you have a blue sky.
Sure.
Visually, of course, you don't want to go any deeper than H alpha, but that works pretty well also.
Okay. The reason you want to pre-focus your eyepiece is because in the bright daylight sky, if you're out of focus, that razor-thin crescent is just going to disappear as it expands. You know, as it expands in the out of focus image, you're never going to see it. So pre-focus on some very distant object, not the sun. Be careful, man. Anyway, that is all. That's my observing challenge. Yes, sir.
I actually do focus on the sun with the sun filter.
You can do that as long as the sun filter doesn't act as a weak lens. You know, some of my filters act like weak lenses. And, you know,
that's what I do. That's what I'm going to do.
Yeah.
Then I'm going to push the telescope to move away from the sun.
Yep.
And then I take over.
Yes, of course. And no sweeping. Don't be sweeping like crazy. You know, you got to really be careful.
Right. There's another way. You could also put your telescope in the shade of a building.
Yep.
Yes.
And so you would never actually look at there's no possibility of actually looking at the sun.
Yep. Now, on the day of inferior conjunctions, it's directly south of the sun. So that might be an issue, but that's at noontime. But for about 4 or 5 days on either side of inferior conjunction, Venus will be less than 1% illuminated. So it's a pretty cool thing to see if you've never seen it before. So yes, sir.
Just out of curiosity, have you ever seen Mercury in inferior conjunction?
Not in inferior conjunction, no, but I have seen it in the daytime sky. It's a little more challenging to find because it's so tiny, and its brightness is often too faint to see. The other thing with Venus or even Mercury is to catch it when it's on the far side of the sun. But again, you have to, superior conjunction, you have to wait for a good one. So it's well above or below the solar disk. And then it looks tiny because it's really far away, but it's a fully illuminated Venus. It's really kind of cool to look at. And it's just fun.
And that you can do naked eye. If you have a good reference point, sometimes SkyTel will tell you about where it's located in relation to the moon. If you've got a good reference point, if you stare at that point for just long enough, it appears. It's the coolest thing.
Yeah, Venus is easily visible in the daytime sky, usually to the naked eye. You just have to know right where to look for it.
Yeah.
And a lot of people don't seem to be aware of that. And if the moon is nearby, that's a great starting place, because that's easy to find.
Yeah.
Eileen, did you have a
It says
question?
Mercury is there.
Oh yeah, well this is for October 26th. So Mercury is in the evening sky near Jupiter, but again, the ecliptic will make a really low angle to the horizon, making those guys kind of hard to see at night, in twilight. I don't know if you've noticed, but Jupiter's definitely leaving the scene now. I've stopped posting stuff about the Great Red Spot because the window's gotten so tiny that it doesn't seem worth it anymore. But anyway, that's, like I said, that's my challenge for the month. So good luck with that. Be careful. Be careful.
Well, thanks a lot, Rich.
Do you want me to stand up here and wait? Is outreach next? Or?
Let's see what's next.
See what's next.
Old business. Any old business? Does anyone know what old business is, by the way?
Yeah, it's things we've talked about before and you're still talking about.
Okay, new business. At this point, I am going to defer to Mario, who has a short presentation. He's promised it's very short. On some of the work that's going on as of good. Let's see. I want to run it.
Okay, I'll talk loud, this one is long. So, when I built this scope, I inquired about a large buyer's gear or any gear that would work, and the price was prohibitive. So I took the 15.5-inch gear that I had from the 16-inch scope, and it worked fine. It's just every once in a while there's a slippage. The clutch really isn't designed for something this massive. So where's the advancer? Spacebar? Oh, okay, fine. So Byers, he's 91 years old now, and he kind of like is a mother with chickens that have gone off and keeps track of everything. It's amazing. So I actually inquired about what the price would be a few years back. It was still kind of prohibitive. Just to put things in perspective, Mathis, which makes the second best gears for a 20-inch, wants $10,000. It gets kind of pricey. So out of the blue at the beginning of the summer, I get this email from Byers, and he said he's liquidating his company by October, right now. And, excuse me, he said he knew I'd still be interested in a large gear. And this was 8 in the morning. It's 5 o'clock in California when I got this. So he said, call me now. I said, what, are you up now? And he goes, I go to work at 4:30 every morning, Sonny. Well, he actually gave the company to his son. His son was in an auto accident, died, and took it over again. But he's 91, he's liquidating his company. And apparently someone ordered this gear, piece of work, several years ago, never picked it up. So he offered it to me for just $3,000. This sounds pricey, but for a $12,000 gear for $3,000, I said sold. So he sent it to me, and it is a beautiful piece of work, incredibly well machined. So this past Saturday, we had a work party. People, Callan and Corey were there, and other friends of mine from the local astronomy club as well. And this is the old gear, 15.5 inches. It doesn't sound like much going from 15.5 to 23, but when you see it, it is massive. It's 4 times heavier, 4 times, I mean, it's just incredible. So first thing we had to do is we lifted it up because you couldn't get to the gear any other way. It's quarried. So we lifted it up, now it's above the floor level. And I had pre-decided I'm going to leave it at that level. This way, well, you've been there, so you know when you're looking at the Veil Nebula, you kind of have to get on the ground and you're only inches off the ground. I mean, it beats climbing a ladder to the stratosphere, but it's still annoying, and I'm getting older, so I decided I'm going to leave it at that level. So we got an extra 18 inches now. So now, for 90% of the sky, it's easy to get to. But looking at the horizon, you just got to go up 2 steps. That's fine. So built a new stand for it that's going to be above grade. And then we had to support it properly, the lift in multiple areas so that we could take off the gear, since, as I told everyone at the beginning, the main job today is not drop the telescope. And we supported it in 4 points. And now we're finally ready to take off the south polar axle. Don't forget, that's a thrust bearing. We don't want it falling down. That's the scary part for me. And here it is, floating in space. A little scary. I made a new base for it while I had it apart. And that's all the rigging to hold it in place so it didn't shift. And that's the new gear. It is massive. Notice the other thing too is I always thought that I have occasional track and error and I occasionally lose a sub, and I think it's because the clutch slips. It has 6 of these points to tighten the clutch. This one has 16. And just as a test, I just hand tightened them and I can move the whole scope by hand, just the increased torque because it's so much bigger. So that's securing the big scope. And notice there's a little gap here. It did show up in the photo. So the old gear, it turned out was 3.41 inside diameter, and this is 3.5. So literally, and I wasn't aware of that at the last minute, Alan says we have to do a shim. So out of a solid chunk of aluminum, we did a 39 thousandths thick, well actually it's half that because that's the full diameter. It's a basically a 20 thousandths thick aluminum shim that fit like a glove. Thank you, Alan. I couldn't have done it myself. So there it is installed. We're putting on the Timken thrust bearing, and one of the people who was there put a little summary slide. And I'll probably be down for a few more weeks, but hopefully be better and bigger and better than ever. It is beautiful. Even if it wasn't a gear, I'd buy it just because.
Long. I'm a little challenged tonight. So we're going. So is there any other new business? Yes, Burt.
You may have heard already, former member Don Delworth, lens designer, is retired. He donated his dome to us some years ago. He now has his 16-inch relay telescope. It was in the 1960s that he introduced the concept using a Mangan mirror for a corrector, and he's looking for a home for it.
Hadn't heard of that, so it's certainly something we can look into, but I do remember Don Dillman, so great. Hopefully that won't be old business next year. Any other questions, comments before we get on to the main event? All right, thank you. So, let me just, while we're getting set up, I want to thank Dr. Jennifer Burt again for coming to speak to us today. She's Torres Postdoctoral Fellow at the MIT Kavli Institute.
I think anyway, I'm not really sure.
Kavli, thank you. She received her BA in astronomy at Cornell University in 2010, and she switched coasts to pursue a PhD in astronomy and astrophysics at the University of California, Santa Cruz, working with Greg Laughlin and Steve Vogt on the commissioning and first science applications of the automated planet finding telescope at the Lake Observatory. In 2016, she moved back to the West Coast and joined MIT as a Torres Postdoctoral Fellow. And she focuses, no pun intended, I guess, right, on precision radial velocity measurements of exoplanets. So I'd love for you to, well, before we go any farther, I always like to compare my publications to everyone else. Dr. Burt has 38 publications or articles, and Google Scholar has a cool function. You can go and click on someone, and you can look at the number of citations that a person might have due to their publications. And since 2013, she has 325 citations. This means that people have actually read her papers and actually cite them in their work, which is really exciting. And she's on a logarithmic approach, where with my publications, they're reverse logarithmic. So I want you to welcome Dr. Burt, and we're really excited to have her.
Much too generous, because my actual first author papers are all about automating this one telescope and no one cares. But I'm on a bunch of things that I take data for other people, so it works well.
I'm going to switch the lighting on just for a second.
Okay.
Okay, thank you.
Cool. Well, yeah, thank you so much for having me and for trekking out in the rain and kind of terrible weather that we had today. It means a lot that the room is not empty, given how nasty it was outside. I'm really excited to be here and to be speaking to you all today. I'm going to take the next chunk of your evening and tell you all about the work that we're doing with the TESS satellite, NASA's newest exoplanet hunting mission, which stands for Transiting Exoplanet Survey Satellite. Okay. So it turns out that nowadays we know about a fair number of exoplanets. We have discovered literally thousands of them. This is not really a new field anymore. Many of those are shown here in this third edition of what's called the Kepler Orrery. And so this shows the many hundreds of transiting planet systems that were discovered by NASA's Kepler mission, which is kind of TESS's big brother. Each of these sets of circles depicts a real planetary system discovered by Kepler, where the sizes of the planet orbits are done to scale, as are the sizes of the different planet circles. And so you can see that there's this incredible diversity of systems that were found by just this one mission over the course of its 4-year survey.
Like a lead person made that graphic.
It's even better. I specifically muted because it plays off Flight of the Valkyries in the normal YouTube video, and here's where when you forget to hit mute, then it is a startling thing. So all told, we now know about more than 3,000 confirmed exoplanets. And in that pile, we've got nearby planets, like the one that was found around Proxima Centauri, which is literally the closest star to us. We've got faraway planets that are orbiting stars on the other end of the Milky Way from us. We've got big planets like WOP-17b, which is notably larger than our own Jupiter. We've got small planets, ones that are in between the Moon and Mercury, like Kepler-37b. We've got multiple planets orbiting one star, like these 7 planets that are going around TRAPPIST-1. We've got one planet orbiting multiple stars, with the kind of confirmation of Tatooine being a thing that happened with Kepler-47. We have planets that are too hot, and planets that are too cold, and maybe even some planets that are just right. So how did we get to this point of having this sudden pileup of worlds beyond our own solar system? Well, if we step back and look at how the sample was built up, we can see that the field of exoplanet detection is a relatively young one. In that if I make a graph of the total number of known exoplanets as a function of discovery year, it goes back only until kind of the late 1980s. It turns out that up until 1995, we didn't actually know whether or not planets existed around other main sequence stars in the Milky Way. While it seemed likely that the same formation and evolution processes that shaped our own solar system were at play elsewhere in the galaxy, we didn't actually have something we could point to. We were kind of stuck with this sample size of 1 being our own solar system, our planets orbiting around the sun. So that made it hard to understand, in general, how planets come to be. But then, in 1995, astronomers working with the TNG telescope in the Canary Islands detected something. And suddenly our count doubled, and our sample size went all the way up to 2 known planetary systems. Which is like, a factor of 100 increase, which is really a nicer and kind of more compelling way to state that, then it went up by 1. But this new system didn't actually do much to help our understanding of planet formation and evolution because it looked absolutely nothing like any of the planets in our solar system. So the first planet we found outside of our own was 51 Peg-b. So this is what is now known commonly to be called a hot Jupiter. It's a planet that's roughly the size of Jupiter, in this case actually a little larger. It's something like 50% more massive than Jupiter, 50% larger, but a little less massive. It's less dense than Jupiter is. And it's going around its star in a 3 or 4 day orbit. So it is this giant planet that is being heavily irradiated by its host star and just whipping around it faster than anything we thought was possible based on looking at our own solar system, where the shortest period planet is Mercury, which is still on an 88-day orbit. So this didn't really help us kind of sort out what other planetary systems look like. In fact, when they first found the data, when they first looked at the data for 51 Peg-b, the folks who ended up publishing and discovering it sat on it for a while because they were so convinced that this kind of planet just shouldn't exist. But once this discovery got out and everyone kind of verified that yes, it looked like it really was a planet despite how strange it was compared to our little local neighborhood, the search expanded. And people across the globe started monitoring the brightest stars in the night sky, looking for signs of planetary companions. Now, over the next decade, we slowly expanded our pile of exoplanets, adding more and more worlds to our exoplanetary census. And so, if you look between 1995 and kind of 2006, we get up to roughly 100 known exoplanets. And that are discovered in, a variety of ways. There are some different colors here corresponding to different detection methods shown on the top left of the plot. But you can see that the majority of them are found in this red, which means they're radial velocity detections. But it turns out that 100 planets, while it sounds way more impressive than 1, is still a relatively small sample size to try and draw conclusions about planet formation and evolution from. Especially when we know already that it's a very diverse set of objects we're seeing in those 100 detections. Now, it's only in the past decade that we've really reached a number of planets where we can start understanding these underlying physical processes that help form the planets. So as of, 2017, we're up to 3,400 or so confirmed exoplanets. You can see that there are really 2 main colors, 2 main detection methods that dominate this histogram. There are the radial velocity detections in red and the transit detections in green. And so I'm going to take a moment to kind of walk you through those now to talk about what we can learn from each method, and then later on we'll say what we're kind of understanding now about our galaxy based on them. So the first one, the method that kind of started it all, is radial velocity detection. This is actually what my PhD was in and what I do nowadays for a living. And so this method is built around the idea of studying the spectrum of a star. So taking the light from a star and splitting it into a rainbow, just like what happens when you shine light through a prism or through like a sun catcher that you would hang in your window at home in your kitchen. So this is an actual spectrum of the sun taken by the APF, by the Automated Planet Finder. This is my baby out in California, the telescope that I spent most of my thesis working with. And what we do with the APF is that we take the light from a star and we split it into its component rainbow sections. In this case, this is light from the sun. As someone mentioned earlier, one needs to be careful and one should probably not point a 2.4 meter telescope at the sun. So I think this is actually a spectrum taken off of the moon, because BJ was lovely and did not melt our telescope by pointing at it, at noon. So you can see here that we get that same kind of nice rainbow distribution. We start with the red up at the top, move our way down to the blue and kind of violet side of the spectrum at the bottom. And in addition to the nice colors, you can also see all of these black absorption lines that are showing up in the spectrum. Now, those absorption lines happen because while the inside, very hot interior section of a star forms a continuous rainbow, when those photons leave the star to start making their way towards us here on Earth, they pass through the outer, cooler layers of the star's atmosphere. The different elements and molecules that live in that cooler part of the atmosphere absorb very specific parts of the light. So it's like having a fingerprint. Okay? Now, by looking at the spectrum of a star and noticing exactly where the lines show up, we can trace that back to identify the component atoms and molecules in the star's atmosphere. So when we see two dark lines in kind of the yellow to orange region, that's probably due to sodium. This narrow doublet in the green is due to magnesium. There are a bunch of iron lines everywhere in the visible spectrum. And so this is a really nice way to understand the chemical makeup of a star, and it can give you hints about things like how the star was formed and how old it might be. But what I'm most interested in and what radial velocity detections depend on is looking for these lines to move back and forth. Because if a star is kind of sitting in space and minding its own business, it turns out that these lines don't do much. They sit there, they tell you what's in the star, and that's great. But if the star is moving, we see something a little more interesting. So who knows what a Doppler shift is and what kind of the canonical example is?
Train horn.
I love it when people say train and not car because my slides look so much better. Yeah, so Doppler shift is what we think of when a train or an ambulance or anything with a siren goes by. And so basically, if your train is emitting noise and it's moving kind of forward, then the sound waves in the motion of direction get scrunched together, they move to a higher pitch, and then the sound waves that are moving away from the train, behind it are stretching out because your source is moving away from them. Okay? So you have high pitch on the right, low pitch on the left. Now this same idea, the movement of a source affecting the pitch or the frequency of the waves that it's emitting, also applies to light. So if you have a star that's moving towards you, the light gets scrunched together, it gets blue shifted. And if you have a star moving away from you, then the light gets spread out and it gets red shifted. One of the reasons, or one of the places we see this in astronomy is if there's a planet orbiting around the star. Because while the example we tend to think of is that the star sits in the middle and the planet goes around it in a nice circle, what actually happens is there's a common center of mass between those two bodies and they're each moving around it. So the star is moving on a circle with the same period as the planet but much smaller. So it sits in the middle and does kind of like a little hula hoop motion as the planet goes around. What that means is that the star moves towards us and blue shifts its light and then moves away from us and red shifts its light, and it just does that over and over and over again as the planet makes many orbits until you can start tracing out that periodicity. So, there we go, yeah. So here's an animation that kind of exaggerates it, but it gives you an idea what's happening. So as the planet moves around the star makes its own little circle. As the star is coming towards us here, we see the lines blue shift, and as the star moving away from us, the lines red shift. If you were to map out the movement of those absorption lines in the star, you can measure how far they shift in wavelength space, and then you can turn that into a measurement of the velocity of the star based on the speed of light. And so what happens then is we map out something called the velocity semi-amplitude or the radial velocity semi-amplitude. And if the movement of the star is caused by a planet going around it, you should get a nice sine curve. Okay? So as the star is coming towards us, you get a blue part of your sine curve, and it's moving away from us, you get a red part. And the period of that sine curve tells you how long it takes the planet to go around the host star, and the amplitude of the sine curve lets you back out how massive the planet is. Okay, so that's radial velocity in a nutshell. The other method that shows up a lot is the transit method. And so this is the idea that if you have a planet going across a star, it blocks out a portion of the star's light. A bigger planet blocks out a larger portion, so you get a larger dip. So again, this is the kind of basic concept. If the star is sitting in space and minding its own business, it doesn't change very much, which is a very generous exaggeration. But so the starlight, the brightness is relatively flat until a planet comes and gets in the way. Now, from the size of that depth, the change in flux, we can back out the relative areas of the planet and the star. That lets us then back out the radius of the planet if we know how big the star is. And from there, we can start talking about the size of the planet and what volume it encompasses. Now, it's not quite that simple because almost all stars are active. That idea of, oh, the brightness is just a straight line is not true. And so, as an example, this is the Pleiades cluster. Yeah, there we go. Which was observed by K2, which was the continuation of the Kepler mission. And they sat on these 7 different stars that make up this constellation and measured what their flux was doing, what their light was doing over time. And you can see that none of these stars present a straight line in how bright they are. We see long variations in Maya that look kind of nice and sinusoidal. We see these kind of diminishing and then amplifying again waves in Robi. We see kind of funny heartbeat patterns up in Atlas. So every star in the sky is doing something funny in terms of how bright it is. It's not a good assumption to think that your star is just kind of being well behaved and quiet and not messing with its brightness over time. And even when the stars aren't super active, even if they're kind of slowly changing such that you could fit out the activity of the star, there's still a lot of smaller structure and variation on their surfaces. So this is an actual video of Venus moving across the surface of the sun, Mercury moving across the surface of the sun when it transited a couple years ago. And you can see that the size of the planet is actually comparable to many of the kind of plage and faculae and star spot features on the surface of the star. So a star is not a nice, like, homogeneous brightness. You have to account for the fact that your planet can be transiting across structure. But we can still do science with this. So this is an actual light curve of a star. You can see the activity of the star, the fact that it's changing in brightness as kind of the large-scale structure of the dense part of the curve. And then these dots coming down in the areas I've highlighted in red are transits of the planet. From the spacing, the timing between these transits, I can back out what the period of the planet is, how long it takes to go around the star. And from the depth of the transit, I can, again, back out how large the planet is. Okay? So, comparing these two methods, from radial velocities, I can learn the mass of the planet, the orbital period, and the eccentricity of the orbit, if it's circular or more of an ellipse. And from transitometry, I can learn the radius of the planet, again, the orbital period, and its inclination, how far off the central chord of the star it is. Now, both of these are what we call indirect detection methods. We never actually see the planet itself. We see the effect that the planet has on the host star. Okay? So we are inferring everything about the planet based on what the star is doing. We're not actually watching the planet have these effects itself. Okay, so basic overview of the 2 main methods that we use to search for exoplanets. Now that we've got those out, here's that current composition of confirmed exoplanets shown in a slightly more quantitative way than what I did before. So again, this is the 3,500 or so confirmed exoplanets that we have, plotted with their orbital period on the x-axis, how long it takes to go around the star, and their radius on the y-axis in Earth radii. Okay? So now that we have this large and kind of expansive pile of planets, we've learned some cool things. The first is that exoplanets are super common. I think when this field got started, there was kind of a concern that, like, maybe there would only be, 3 other planets out there, and what would happen? We wouldn't be able to learn things. No, they are everywhere. At this point, you cannot swing a stick in this galaxy without hitting a star that has planets around it. Much of the time when trying to measure the mass of a planet, it turns out that the star you're observing actually has more than one planet, and then the signals get really complicated. And what I would give for a star with just one planet where I can measure a nice sine curve and be done. So yeah, it's actually getting a little crowded out there, which is like not a thing I should complain about. It is the reason I will probably get to keep doing my job for many years. So honestly, I'm excited about the planets, but they are everywhere. Okay, the second thing is that of these 3,500 confirmed planets, you can see from this graph that the vast majority of them exist in this space between the size of Earth and Neptune. Which planets in our galaxy are between the size of Earth and Neptune? Okay, correct answer, none of them. We don't have anything that lives in here. So the most common type of planet, the thing that seems to be the archetype of planet formation in the Milky Way, produces an object that we don't have in our solar system. Now that could be an observational bias. It might just be that we haven't been looking hard enough or at exactly the right stars to see lots of planets just like the Earth and Neptune. Or it might say something funny about us, and we're still trying to figure that out. But basically, this seems to be the dominant mode of planet formation, and we don't have a local example to go and poke to figure out what these objects might be. Yeah?
Why is it a double cluster? I would have thought it would be a continuous...
We don't know. Basically, yeah, we see objects that look like the ice giants in our own solar system, kind of these, we call them sub-Neptune type things. And then we do see some kind of Saturn type objects, which fill the gap that you're talking about. Whether or not there's actually a paucity of Saturn type objects, or if it's just an observational bias, is something we're not entirely clear on yet. So it's, many questions come from this plot. But yeah, so we're trying to figure out basically if these objects are scaled up versions of the Earth, so like really rocky kind of metal core based objects with very large mantles, or if they're scaled down versions of Neptune. And this is one of the questions that has just gripped the exoplanet community over the past few years. So that's a whirlwind overview of where we stand with exoplanets at the moment. And now reaching back to my title slide, what is TESS and what is it going to do and why is it relevant to all of this? Well, to give you a little bit of context, I'm going to first talk about TESS's predecessor. This is, again, the Kepler mission, which then became K2 in the kind of latter part of its life. And so these are a mission that was set up by NASA for a 4-year transit survey looking at this one section of Cygnus in the northern hemisphere. And Kepler's whole job was to try and understand how common Earth-like planets around sun-like stars were in the galaxy. So how often do we see ourselves elsewhere in the Milky Way? Kepler found most of those thousands of planets that I showed you earlier and did a wonderful job of surveying stars within the Milky Way. Whoop. Oh no, I lost it. Okay. But unfortunately, it turns out that the vast majority of the planets found by Kepler are actually too faint to then go and try and get masses of. Because what we'd really like to do moving forward with planets is not just find them. There are some cynical folks who refer to detecting a new planet nowadays as kind of like stamp collecting. You have 3,500 of them, why in the world would you care about finding one more? And I get it, like there are a lot of them nowadays and maybe each new planet isn't quite as exciting as it was back in the 1990s. But the thing that we're kind of moving towards is instead of just detecting planets, we want planets that we can characterize. We want to be able to say more about the planet than just knowing it exists and maybe being able to figure out how big it is, which is what we can do with Kepler from that transit method. We want planets where we can do transit detections and radial velocity follow-up and then put those two together so that you have a mass and a radius of the planet, and then you can start trying to understand what its bulk density and possible composition is. What might these planets be made out of? Now, it turns out that on this plot, which is from, I think, 2016, if I'm correct, you can see that the number of planets for which we have both a mass and a radius, and can therefore talk about what they might be made out of, is relatively small. Okay? And from 3,500 known exoplanets to like 12 on this plot. And that's a bit of a scaling down. So basically, the challenge here is that to do radial velocity follow-up to try and measure masses for planets, they need to be orbiting very bright stars. Because you need to take the light from that star and spread it into this very finely sampled rainbow spectrum that I mentioned earlier. So up here you can see the small number of planets we have to try and map out what's happening here, but because we don't have many data points yet, it's hard to understand which types of composition, things that are 50% rock and 50% silicate, so kind of dirt and clay on top, versus 100% rocky material versus things that have voluminous outer atmospheres of water or hydrogen or helium. How common are these different types of planets? So the stars are too faint because Kepler targeted a small patch of the sky, and when you do that, you're going to be dominated mostly by relatively faint stars. Fortunately, TESS, the whole mission, is to come after Kepler. So Kepler went up and said, yes, planets are everywhere. If you design a new mission and point it anywhere in the sky, it will find planets. Don't worry about that part. So TESS's job is now to do exactly that. It's going to survey the whole night sky, starting in the southern hemisphere and then switching to the north, and look for planets on the closest, brightest stars. The kinds of planets that we have the best chance of doing detailed characterization and follow-up of. So we want to go and figure out what they're made out of. Now, the stars that TESS is observing aren't intrinsically different than what Kepler looked at. They're just closer. So you can think about it like this. If there's us with the sun sitting on the Earth, Kepler's observing scheme was to stare at this one patch of the sky, which means it basically formed a cone looking out at stars that were up to 3,000 light years away over a very small fraction. Something like 0.25% of the night sky. TESS is instead going to look in all directions, but in a very kind of volume-limited survey. It's going to look at stars that are roughly within 300 light years or so. And what this means is the TESS stars on average are going to be something like 10 times closer and 100 times brighter than what Kepler looked at, which is great. We're going to have a sample of planets around bright stars that mean we can then go and do interesting follow-up of them. Okay, so the basic schematics of the mission itself, TESS looks like this. It's got big solar arrays that are what power it. It's got a combination of 4 cameras, that I'll show you in a second, that are kind of inside this shielded upper area with the sunshade around it. It's got the antenna that it uses to downlink data back to NASA and MIT, thermal blankets to help keep it well insulated and stable in temperature, and then the reaction wheels that help it point really finely. If we peer into the satellite, movie's good. Forgot that was a movie. Then it looks like this. This is the beauty shot that they put together for TESS that gives you a nice rotation. So again, here are the solar panels. Here's that antenna that lets it send information back to us on Earth. And then, if it comes back around, these are the 4 cameras that it uses. Each camera has a lens that's only about 10 centimeters wide. It has 7 optical elements. These were designed and built at MIT. There we go. Yeah, so these are kind of, to give you a sense, the cameras are kind of this big, which is a very well quantified scale. This is Sorbet helping with the installation and testing of the cameras. These are the big kind of cryogenic cells or tanks that they were put in, so we could, in the MIT labs, pump them down roughly to the temperatures and pressures we would expect them to experience in space and make sure they still worked. So each camera, and it's a little hard to see here. This is the camera that's in this, the lens in the telescope. Sorry, the detector that's in the telescope is built of 4 individual detectors, and they have a field of view on the night sky that's roughly 24 degrees on a side. For reference, I probably don't need to tell you guys this actually. Most astronomers, you're like 24 degrees on the night sky, and we don't actually know how large that is because people just hand us data products. But no, so 24 degrees is roughly the size of Orion. So each camera looks at Orion on the night sky. This is fun. This is, you don't want to play? There you go. So this is just a little video that shows some of the integration and testing again with that beauty shot that they made. So these are, we built bits of TESS in different places. Like I said, the cameras got built at MIT. Other parts of it got built at Lincoln Labs. or orbital ATK, who are the folks that eventually put it together. So we had to, once the cameras had all been tested, built, and then chilled and tested, and we thought that they were working well, we had to then ship them to Virginia. So everything got handed down there. This is them installing the 4 cameras into the panel that holds everything steady, make sure they're pointing in the right directions and such. Apparently this took like hours. Getting that aligned just right was a very non-trivial process. It took a long time and like 7 people, all very carefully moving the lenses in and out. Yeah, they sped this up and it still takes forever in the video. So it was a kind of nerve-wracking few days is my understanding of things. But yeah, so here are all the cameras. These are wrapped in their little thermal blankets, the silver things to help keep them, because in space the temperature varies by hundreds of degrees based on whether or not the sun is shining on you, so you want to make sure that cameras don't see so much of that change. Okay, so everything ends up being very shiny by the end. Here we go. Yeah, and so then once the cameras are mounted, they then join that to the rest of the satellite. Okay, and again, this goes in sped up motion, but it still takes a while. Okay, we'll talk about the observing planet in a minute. So it turns out that TESS is actually not that large. There's a full-scale replica of it in my office, well, in like the office area I work in at MIT. It comes up to about here. So TESS is roughly 5 feet tall or so. It's not actually a huge spacecraft. When they were thinking about how to put it into space, they put a couple of bids out, and the folks that won were SpaceX and their Falcon 9 rocket. So the only bit of the rocket that's actually holding things is the fairing up at the top, which looks something like this. And if you compare the size of the fairing to the size of TESS, it is this
Wow.
Yeah, but they were the cheapest option and did a very good job of like kind of saying, here's how we'll do the best science for you. So good on it. And indeed, so this is down Cape Canaveral. This is TESS getting put into this giant fairing. I imagine she was lonely in there. Yeah, and this is them kind of shipping, like, this thing is huge, look at these people next to it. And Tess is like this big. She's just not a big lady. But yeah, so this is the fairing once it was all sealed up. And then this is a picture of the rocket going up. From where I was sitting at this launch, you could like, the rocket was like this big, way on the horizon. It turns out it was on the furthest launch pad, I think, possible from where we were all sitting at Cape Canaveral, so. But it was still really cool. You could like feel the wave as the rocket went up, which was a fun experience. Okay, so what is TESS gonna look at, or rather, how is it gonna look? What is this? Wait, no, do a thing. It's gonna make noise. Okay, so the 4 cameras I mentioned are canted in a funny way, which allows them to then make this kind of rectangle of observing space on the sky. So yeah, the bore sight is tilted from the ecliptic, and so it has a 96-degree field of view. So again, each of these cameras is roughly the size of Orion on the night sky. And then all 4 of them get stacked to make these kind of large columns of observing space. And what TESS does is it looks at one column for roughly a month, and then it turns around, and it's going to show you.
Simple step observation star.
You gotta do the narrating, dude. Oh, whatever. So yeah, it has these sectors. It looks at one for a month, and then it rotates, and then it looks at another one for a month, and it forms this continuous viewing zone down here. Yeah, fine. And then every 2 weeks, it downlinks the data back to us at MIT and to NASA so we can look through it and search for planets. Okay, so what is TESS going to look at? That's kind of how it observes. We're going to talk about what it observes. First, and again, I think people in this room probably need less of this primer, which is great. TESS is going to focus mainly on main sequence stars, so it's going to be looking at things that are still burning hydrogen. So they're kind of the longest and most stable part of their lifetimes. The main distinguishing factor between different main sequence stars is their temperature and therefore what color they are. And so stars that are hotter and brighter tend to be blue, and stars that are cooler and tend to be red. And so this plot shows roughly the type of light that is emitted if you assume stars are black bodies, which is a decent assumption. So G stars, like the sun, emit the peak or the most of their flux in the green part of the spectrum, whereas cooler stars like M dwarfs emit mostly in the red and infrared. This is The fact that the human eye is most sensitive in the green is not a fluke, right? So here's eye color sensitivity as a function of wavelength. You'll note that human eyes are very good at seeing green light. And that is likely an evolutionary thing because there's a chance that, you had ancestors who saw better in not the green part of the spectrum, and then they got eaten. You didn't get to make babies. So the fact that we have evolved to see very well in the peak wavelength emitted by our host star is probably not that surprising. Okay, so TESS is going to focus on M stars. It's going to look at these cooler, fainter stars. And so as a kind of comparison, this is Kepler's curve of what wavelengths it was most sensitive to. And you can see that Kepler was designed kind of to peak more in the 600 to 700 wavelength regime, the greenish part of the spectrum. Which makes sense because Kepler was designed to look for Earth around the sun. So Kepler's job was to look mostly at sun-like stars. TESS is going to look at M dwarfs, and because of that, its peak is, it does start at 600, but it stretches much more onto the red side. And you can see that the M stars kind of just gain in flux as you go redder. So why M stars? Why are these the things that we're choosing to target? What's wrong with stars like the sun? Well, the first one is the first reason is because there are a lot of M stars nearby. So this is a lovely shot of the night sky in the visible part of the spectrum. So this is what you and I would see if we went out somewhere that was really dark and had great seeing. Turns out that M stars, these red stars, are more common than kind of bluer, greener stars like the sun by a factor of roughly 10. So if I switch this filter to instead show what happens if you look in the infrared, there we go. All of a sudden, in the infrared, the M stars really pop, and you can see just how common they are. Steve used to call them, I think, the vermin of the skies, because they're just kind of everywhere. Okay, so again, hard to swing a stick without hitting an M star. So, reason one, they are very common, they are everywhere, that's great. The second reason is that in transit detections, it's much easier to see the transit of a small planet around a small star. So because the dip you get in the brightness of the star is just that ratio of the sizes, the our planet over our star fraction I showed you earlier, if our star is very big, that fraction is a small number. If our star is a tenth the size of the sun, all of a sudden that fraction is a much bigger number and transit becomes much more obvious. You're blocking 10% of the light from a star versus 1% of the light from a star makes it much easier to see. And the same kind of effect comes in with the radial velocities as well. The planet can pull much harder, it can have a much bigger effect on a star that is smaller. So the planet's gravitational effect scales as 1 over the mass of the star to the 2/3. And so less massive stars means bigger RV shift. Okay. And then the third reason is that planets in the habitable zone, this idea of being in kind of like the just right section around a star where you could maybe have liquid water based on how hot the planet is from the star's insolation. That region is much closer around M stars because they're emitting less energy and how do I say this? Longer wavelength energy, so they're emitting more again in the infrared as opposed to like the UV and the visible. Then this region of space is much closer to the star, which means the planets are on shorter orbits, which makes them again easier to see both in transits and in radial velocity. So for example, this is our solar system and kind of our habitable zone shown here in green. So Venus is a little too close to the sun, Mars is a little too far away. They're both on the edges of the habitable zone, and Earth is kind of happily chilling in the middle. If we compare our habitable zone around a sun-like star to the habitable zone of TRAPPIST-1, which is a very, very small, very cool M dwarf. Okay, so the TRAPPIST-1 system, which all 7 planets and the star fit here. Okay, so again, this is the one where like the longest period planet's only like a 20-day orbit. The planets here, D, E, F, and G, that are possibly within the habitable zone of the TRAPPIST system, have D has a planet of 6 days, and G has a planet of 12, I think. Okay, so again, if we want to talk about which planets could potentially have liquid water, could potentially host life, we're now looking for planets that go around the star every like 8 to 10 days. That's a lot easier to find. And so all of these factors make M star super desirable for TESS. And in fact, you can see that the number of targets TESS is observing. Here's the effective temperature. So this is kind of sun-like stars here. This big peak over here, like 3,200 degrees, these are all M stars. So TESS is designed to really go after those. Okay, so what will TESS find? This is a histogram of the predicted planet detections from TESS that was made back in 2015. So this has different kinds of planets on the x-axis: Earth planets, super-Earths, sub-Neptunes, giant planets, and the number we expect to find. And you can see that for the Earths and super-Earths, we're looking at hopefully some hundreds, like 400 or 500 Earth-type planets. Another, 1,000 or so once we start using the full-frame images of TESS in the sub-Neptunes, and then thousands of giant planets. So the goal is that TESS will just like fill our understanding of planets around nearby stars, and that'll be really great. If you look at how those planets are distributed on the sky, you can see some hints of that observing design we talked about earlier, where the overlap zone TESS has, where one camera just sits in the same space, shows up here because there are more planets detected in that polar region, and then it kind of spreads upwards. We specifically skipped where the galaxy goes through this plot because the stars there are so crowded, it's really hard to discern individual stars because the TESS pixels are very large on the sky. Each TESS pixel is something like 21 arcseconds on a side. Especially if you look at the galaxy, you're going to have a lot of stars falling into that space. Okay. This is fun. So this is a zoom out, once I hit go, of the expected planets from TESS. And so what's happening here is we are looking down on the solar system. Our sun is kind of right at the middle of this X. And then we're going to slowly zoom outwards. And you're going to see planets that were found by Kepler in black. Other planets we know about the transit found by not Kepler in blue. And then the predicted planets from TESS in orange. Okay, cool. So, as we start zooming out, we get up to 3 parsecs, which is kind of the very local neighborhood still. We can see our very first TESS planet showing up, our predicted TESS planet. These aren't real, but it's what we would expect based on our knowledge of how common planets are and what kind of stars are nearby. Showing up at like 3 or 4 parsecs. Okay, so score 1 for TESS. No other planets in the picture yet. Okay, so again, emphasis on bright nearby things really showing up early. We keep zooming out, we get to 10 parsecs. A little further, there we go. And to 30, you can see that there are a few planets that have been found in blue by non-Kepler type things. These are WASP and HAT and Corot and other missions that have been searching for transiting planets on nearby stars. I keep zooming out. By the time we get to about 100 parsecs, and this is again that roughly 300 light year-ish range that TESS is looking for, you can see that this diagram is just swamped by orange points, right? There is so much orange on this picture because again, TESS is focusing on bright nearby stars. If I let this run further out, you can then start to understand again that shape of what Kepler looked at. Okay, so can you get? Oh, darn it! Do it again. Yeah. So when we get to again, can you guess which direction Kepler was looking? It's a question I was going to ask. Yeah, so you can really see the structure of how the 2 missions compare because TESS again has this kind of nice circular, blob of stars that are nearby and bright, which is great. And then Kepler is like, I will just look in this direction for forever. Find all of the stars that happen to be in Cygnus. Okay. So what are we going to do with all these planets? TESS is going to find hopefully thousands of new things. We're going to add them to our pile of thousands of planets that we already know about. Why? What is the science pitch behind all of this? Basically, we're going to try to learn more about them. We're going to take advantage of the fact that TESS is finding planets around bright stars. We're going to characterize them. We're going to try and understand what they're made out of and how they evolved and what their compositions might be. Turns out that just by being able to better classify the stellar host, by having stars that are bright enough to take nice spectra and really measure things like what the effective temperature of the stars and what its metallicity is and how big the star is, we can do a better job of understanding the exoplanets that orbit around them. Because again, these are indirect detection methods, so when we measure the size of a star, what we're actually measuring is how the radius of the size of a planet. What we're actually measuring is how the radius of the planet compares to the radius of the star. Okay? So it turns out that by some great work done by B.J. Fulton last year, we now know that when you look at those small exoplanets, the ones I said were the most common type of planet anywhere in the galaxy, as far as we can tell so far, it's not actually just like one big lump of planets below, 3 to 4 Earth radii. We see a bimodal distribution. We see planets that are kind of 2 to 3 Earth radii, and then like 1.5 and below. And we think that this gap, the Fulton gap as it has been called, is tracing some aspect of planet evolution. This is giving us hints about how these planets form and how they evolve. It's telling us something relatively fundamental about planets in the galaxy. So we need to do a better job of understanding the host stars of the planets, which is again easier when they are bright. We need to be able to use radial velocity detections using telescopes like the Automated Planet Finder, this pretty telescope right here, to go and measure masses of planets and try to get masses that have uncertainties at only the 10% level, which is a very challenging thing to do for many of the transiting planets we have right now, again, because they're faint. But if we can get masses that we know to about 10%, then we can really start distinguishing between what the different compositions of the planet could be. Mass and radius gives us a density, gives us a composition, and our first guess at what the planet's made out of. And that's important because it means TESS can act as a finder scope for future missions like the upcoming James Webb Space Telescope, which will allow us to study the atmospheres of exoplanets. Compared to TESS, James Webb is huge. So here are humans, and here's the mirror of James Webb. This thing is enormous. It's going to be one of our best ways to peer into the atmospheres of these planets and really characterize what kinds of gases exist there. But time on James Webb is stupidly competitive. There's not a ton of it. People are going to be fighting over what we observe. And so you need to make sure you have a very well-curated target list. Okay? We want to make sure we're only spending James Webb time on the best and the brightest and the most promising planets, and many of those are likely to come from TESS. So TESS goes up first. It helps to find the best planets that James Webb could look at, and then when James Webb eventually launches, it will know where to look and where to spend its time. Okay? So, and we'll do that study of the atmosphere using this thing called transmission spectroscopy. So this is the idea of measuring the transit curve of a planet in different colors and different wavelength bands and looking for it to change.
Is also important. To figure this out, astronomers observe the transit at many different wavelengths. At wavelengths
let this guy talk for me, that's right.
the planet will appear larger, with a change in size indicating how deeply the atmosphere extends, and its density at different altitudes. Measuring the depth of absorption at each wavelength gives astronomers the planet's transit depth curve, which allows them to model the composition, height, and density of the atmosphere, providing a detailed picture of the planet. Recent studies suggest that exoplanets and their atmospheres come in a wide variety. At one extreme are hot Jupiters like WASP-19b, a boiling gas giant.
And 51 Peng that we talked about at the beginning.
Then Mercury orbits our sun. Visitors who could survive the heat might complain about the air quality, but WASP-19b's jagged transit depth curve suggests a deep atmosphere of poisonous hydrocarbons, with methane and hydrogen cyanide far more abundant than water. By contrast, planet Gliese 1214b is a comparatively inviting water world. Its nearly flat transit depth curve hints at a shallow atmosphere of pure steam enveloping an ocean thousands of kilometers deep, with an interior of hot ice, water solidified by extreme pressure rather than cold. As detection methods improve, astronomers will search the atmospheres of Earth-sized planets for signs of life such as water vapor, oxygen, and methane, taking us one step closer to finding a world like our own, all thanks to some flickering starlight.
Important disclaimer, we don't actually think most planets are made out of pure water. It is like the part of the density curve that they fit on, but it is much more likely that they are rocky and metal-rich interiors with then big puffy layers of hydrogen and helium on them. So for when people say water world, to be skeptical. Okay, so this is an example of the type of detailed spectra that we could try to get from James Webb. And again, we are looking kind of in the infrared section of wavelength space here. And we would use these spectra, just like that video just showed you, to map out the atoms and molecules that are in the atmospheres of these planets. The other big advance is the creation of the ELTs, the extremely large telescopes. These won't be online for a little while still. So the EELT, the European Extremely Large Telescope, comes online in 2024, hopefully, and the Giant Magellan Telescope in 2025. So we're a little less than a decade out. But these will be one of our first chances to directly image small temperate planets and learn about their atmosphere. So again, Earth-like planets that might be in the habitable zone of their planets, or of their stars. And so that means that for cases where the stars are nearby and the planets are well separated from them, we can even go a step further. And instead of doing transmission spectroscopy, where we're measuring the size of the planet in different wavelength bands, we can try to take pictures of the planet itself via direct imaging. So if you have cases where the star and the planet are far enough away from one another on the sky because they're very close to you, so the angular separation looks large, you can try to separate out just the planet and then study its atmosphere on its own. You're doing direct detections and not this indirect method that we've been talking about with things like radial velocity and transit so far. That's important because looking for water and oxygen isn't actually enough to find ice, or to find life. For a long time, people thought, if you find oxygen, then check, you're good, you found aliens. We think that's not true. There are a number of ways to produce oxygen, even on Earth, that have nothing to do with life, things like volcanoes. And so nowadays, we're actually moving into more detailed studies, looking for things like methane and ethane and N2O and dimethyl sulfide and a number of other what we call biomarker gases that would help to better characterize what you're seeing. Because it turns out that when you're looking for Earth, you really need a very special combination of factors to give you the chance of having life there. So the next decade should hold tons of exciting new discoveries in the field of exoplanets, both on the discovery side from TESS finding things, hopefully thousands of new exoplanets, and the in-depth characterization side, starting with masses from radial velocities and then doing things like atmospheric follow-up with James Webb or direct imaging with the new ground-based extremely large telescopes. And so TESS is hopefully going to be kind of our intro to that. And the process, it turns out, has already started. So this is the really pretty first light image that was released from TESS a few weeks ago now. So TESS is up, she is taking data, she is sending it back to us here on Earth. So this is kind of the proof of yes, all the cameras turned on and are looking great. And then, I'm just really fast. This is one of the first papers that came out on TESS. So this is the pixel map. So this is the detector of one of the cameras. We look at the light from a star that's shown, it's inverted here, so the star is in black. It has a pixel map that looks like that. And if you measure the flux, the brightness in those pixels over time, yes, no? There we go. Okay, you get a light curve that looks like this. Okay, so here's the raw test data up in the top, very top row, and then here's the detrended test data. We've corrected for things like the motion of the spacecraft and the momentum dumps, where it has to send things back to Earth. You see this nice transit showing up over and over and over again. And if you bin that data down, you get this just absolutely beautiful first transit from TESS. So this is a 2 Earth radii planet, it's twice as big as we are, in a 6 and a bit day orbit around its host star. And this is a good group for this. What does it mean when a star has a name that's not like HD, phone number goes here? It's bright, yes. So TESS's first planet is around a star called Pi Mensa. And so Pi Mensa is a naked eye star in the southern hemisphere. It is 5th magnitude. It is so bright that when we tried to look up older images of it, it often saturated the detectors. But this is kind of exactly what TESS is meant to do. It's meant to find small planets around bright stars, and so the fact that its first detection was just checking both those boxes was really nice. This is a star that already had a known planet, so this is the RV data, the radial velocity data, that was taken over decades, and you can see these big variations that look, okay, not so much like a sine curve here because the planet's eccentric, so it's more like a pointy wave. But basically there's a known 10 Jupiter mass planet in a 2,000-day orbit. If you take that planet out and look at the residuals in a periodogram of the data, then there's a big spike that shows up at exactly the period TESS predicts. So basically, the small planet, the little planet on the short orbit, was hiding in the data that had already been taken over the past 20 years. We just didn't know to look for it. And once TESS told us, hey, I think there's a thing here, and we went back, it turns out we could actually map out, here's the sine curve of the planet really nicely. So this was like we measured the mass of a new planet we just discovered without having to take any new data, which is kind of amazing. And this is one of those planets, the reason I mentioned it earlier, borrow this yellow, is at Pi Mensa C, so up there in purple. If you plot it on a mass radius diagram on different composition curves, it sits exactly at a 100% water curve. Again, we do not think this planet is made out of like a giant water droplet. We think it's rocky and iron in the middle and has some fluffy atmosphere, but that is indeed what it sits on, so. Yeah, and the cool thing about it is that if you plot kind of size of planet versus how bright it is in this very sparse region of space where it is, a small planet around a stupidly bright star, which means that we can do all sorts of new and exciting stuff with it. Okay, with that, I have taken more of your time than I intended, and I'm sorry, I get excited about planets. But thank you so much for your attention. Ooh, oh, my turn. And I would love to take any questions you have at this point.
A comment and then a question. So the point that matters, fifth magnitude star. Everyone in this room can get into science and do TESS follow-ups because you already have the equipment.
Yeah, very true.
And the question is, I'm impressed by how many more transits we have in the radial velocity. Because you would think, I know it's easy to do the transits in the radial velocity, but still, you've got so many angles you can do the radial velocity with. I would think you found more radial velocity ones than transits. Why are we not seeing more of the other method?
So the concern you're bringing up is a very valid one about, so for transiting planets, only roughly 10% of stars would be expected to transit, only 10% of planets would be expected to transit their host stars based on just a geometry argument. It has to be aligned correctly for you. The thing that beats that in a scaling order of magnitude sense is that when Kepler was in operation, it looked at 150 stars simultaneously. With RV instruments, you can look at one at a time. And you often need to spend, because you want to average over the activity of the star, all those problematic spikes we showed earlier, for RV you want to spend at least 10 to 15 minutes on a star, and so you can do something like 20 stars a night if you're efficient. And so it's just that the numbers don't work. Like you can only look at one star, and therefore you just scale back so strongly the number of targets you can have. And also, with the transits, and this is, it goes both ways. With the transits, you need to catch the planet at exactly the right point, whereas with the RVs, you need to let the signal slowly build up over time, and so again, that scales in kind of funny ways. Okay, so transit's much more efficient for finding planets, and that's why what's happening nowadays is that we're using things like Kepler and TESS as, again, kind of finder scopes, and then once they find the planet, we go follow it up with RV resources. Yes?
Sarah Lippincott at Swarthmore College, was she using radial velocities or just physical oscillation, physical motion of the stars? I believe that her discoveries, or the team that was working there, most, if not all, of their observations have been discredited. But supposedly in the 1970s and 80s, they did get positive motions, wobbles of stars that seemed to indicate that they were rotating.
Interesting.
Ancient history now.
Yeah, I'm gonna be honest and say I don't know her work. There are two things it could be. It could be the early forms of RV detections, but I don't think they found anything in those days. They tried using earlier methods of what I use now. My guess is maybe it was looking at like 2D motion of the star on the sky, so doing more of like an astrometry approach and looking for giant planets that would be really tugging on things. But I don't know the specific papers. I'd have to look
Actually,
into
they were doing radial velocity.
Oh, it was? Okay, with like the
And
HF cells?
It was with a 24-inch refractor. And the problem is they found, in fact, somebody who came to Swarthmore and worked there with Peter Van de Kamp, who was the person in question.
Oh, I know that name.
He disproved Van de Kamp's work. And so within this it's actually quite small department at Swarthmore, you had two people, one of whom had disproved the life work of another.
Oh no!
So,
Man,
anyways,
coffee hour must have been awkward.
it was an instrumental error, and but it took quite a bit of
Okay.
work and analysis to prove that.
I mean, and this is the struggle with any indirect detection method is that proving you're right is often more a case of disproving the negatives. Did I negate that correctly? You need to do things like you prove that my instrument could not have created the signal and the stellar activity could not have created the signal and the dates and times which I observed could not have created the signal. So you kind of go through and say, it couldn't have been any of these things, and in absence of those, we will assume it is a planet. And what often happens as new techniques come along or better analyses come along is that someone says, oh, but you didn't think to look at, this potential source in exactly the right way, and so now it turns out that was, and then recently this comes up a lot with stellar activity. People think they find planets, and then it turns out that it's actually activity from the star masquerading in some clever way, and it takes a lot of really in-depth analysis to tell that sometimes. I'm gonna go this side of the room and then back.
You mentioned several times that TESS is looking for nearby brighter planets,
Yes.
close to brighter planets. To my mind, those two things don't necessarily go together. I mean, you can have bright stars that are distant
Yep.
and near stars that are dim. I mean, which is it? Is it the brightest or the nearest?
Yeah, so the selection criteria for TESS is kind of a layered thing. It is true that if stars are closer to you, their apparent magnitude is brighter just because of how the light falls off as a function of distance. TESS so it has two observing modes. It can observe stars every 2 minutes, or it can observe stars every half hour. It does the whole field every half hour. And so the stars that get prioritized for the fast observations, for the high cadence work, are stars that are every star brighter than 6th magnitude, I think, is the cut for the bright stars, and then a different set of stars which are more the ones that are really close.
So that's a pre-selected list.
Yes, yeah.
Okay. Thank you.
You.
How are you basing the stellar radii and how accurate are they?
Yeah, so people, they're tricky, it turns out. The biggest source of error in understanding how large a planet is knowing how large the star is. And so we can do it for some cases with having better distances from things like Gaia. So if you know how far the star is, you can calculate, and you know what the effective temperature of the star is, you can then get out, you can know what the luminosity is and back out a radius from that kind of relation. People do different calibrated metrics from like nearby very well-studied stars that say if you know the absolute magnitude in this band and the temperature of the star, then the radius is likely to be X. So
they're estimates based on a number of lots
yeah,
of
it's calibrated to other parameters that are easier to measure for the star for the most part. You can do some star, there are tricky ways to do absolute radius measurements, but it's hard and it doesn't work all the time. It takes a special set of kind of characteristics. So.
Regarding TESS data collection criteria, would that include or exclude close binary star systems?
So they will show up in the full frame images, which are the every half hour TESS just takes a picture of that whole observing field that it has, all 4 cameras. I think that they tried to select against binaries, or for the 2-minute cadence, I think was targeted more towards stars that are not in binary systems, because that gives you a better chance of measuring masses after the fact. So despite the fact that TESS is a photometry like transit mission, its level 1 science goal is to measure the masses of 50 small exoplanets, which is not a thing that TESS can do by itself. TESS needs to find planets and then give them to ground-based RV facilities to do that work. And so with the goal of we need as many candidates as possible to do RVs on, they are, I think, selecting more for single stars.
Is TESS's data being computer analyzed, or is it being analyzed by people like you, professors, or?
It's a little bit of column A, a little bit of column B. So there are 2 pipelines that get run on TESS data. There is the official Spock pipeline, which happens at NASA, and then there is a pipeline that runs on the 30-minute data at MIT. The one I know better is the MIT side because I help with that. Chelsea Wong, who has the office next to mine, has written like the computer pipeline that runs through all of the hundreds of thousands of stars or light curves first, and says it goes through and it flags what it thinks are repeating transit events, and then those all get kind of nice summary slides made and then sent to humans, and we do the vetting to say, do we think this is really a planet, or do we think it's stellar activity that got mischaracterized, or something instrumental from the spacecraft, or contamination from another nearby star, etc.
And then at what point would you contact like either one of the large ground-based telescopes and say, we need to confirm this,
Yep.
or data sources?
So after the human step of the vetting, we go through and say, these are the systems that we think really do look reasonable, and there is a whole TFOP is the Test Follow-Up Observing Program, and so alerts get sent out to folks in that at kind of universities across the world saying, okay, this is the next batch, we think these might be planets, please help us do these 4 or 5 steps that need to happen to confirm or deny that. Now, this has happened once so far. Like, TESS really did just start sending data back, so it's all kind of a work in progress to make sure it goes smoothly, but it's been a success as far as we can tell, so there's no proprietary data. Like the TESS, there's no proprietary period on the data. Once it's vetted and we think we've found things, we send them out to the world and say, please help.
Can amateurs help?
I think there is a plan for that. Certainly, there's like, what is it, KELT? So KELT is the Kilodegree Extremely Little Telescope, is a transit survey that's ground-based. And there's KELT Fun, is the KELT Follow-Up Network. And so like folks involved in that are certainly being tagged to do, to look for like...
the ABSO is in it.
Is it? Oh, cool. Yeah, so folks involved with that can get tagged to try and help do like ground-based photometry of future transits to help better characterize the depth of the transit or what the period of the planet is. And so yeah, it's kind of heavily Karen Collins, who I think is now here. She's got some affiliation with the CFA,
Yes.
but she's not actually physically here.
In Louisville.
Yeah, okay. But she's got some tie to Harvard. Has like an army of people who she manages to like do very clever organizing things with, and they are saving us in many ways. So.
Thank you.
Yeah.
Can you tell me more about the detrending process? What's involved in that? Oh,
I can tell you who to email to ask about that.
Okay.
Yeah. I don't know a ton about it, to be honest. I know that it's mostly to deal with instrument and spacecraft systematics. And so the stellar activity is something like they don't try to take out very much, but we do know specific timescales and shapes of effects that the spacecraft has, and so those we try to remove. But things that are astrophysical in nature tend to get left in, and then we want people to have the whole picture, basically, minus what TESS itself is doing. Yes?
I read that TESS is this really cool, unusual lunar resonant orbit.
It does.
And so it's not going to need to burn much fuel to station people in its orbit.
Yeah.
So does that mean it might be up there for 20 years, effectively?
So that's the goal. TESS's primary mission, as funded by NASA to date, is a 2-year mission. It spends a year looking at the southern hemisphere, it flips upside down, spends a year looking up here. Because TESS is in this very clever orbit where it goes around the Earth roughly every 14 or so days, then it's in this really nice 2-to-1 resonance with the moon, and so the moon's gravity actually like tugs and pushes TESS to keep it relatively stable. And we think that it should be stable for something like 20 years, which means that as long as someone keeps helping to fund the spacecraft, we should be able to just do science for decades, which would be amazing. So the goal is to like knock the socks off of these first 2 years so hard that NASA cannot possibly think it is a good idea to defund TESS. Huh? Yes. We have better reaction wheels than temper. We learned our lesson.
So one of your early slides showed the discovery over time, and it's not very many years, so it's really early in that. So do they have expectations for the trend there? And also, does that mean that distribution you showed in sizes and such might not remain in the distribution?
Yeah, so someone projected forward based on the number of planets that are expected first from TESS and then from a future mission called Plato. By the time TESS finishes its 2-year mission in 2019, 2020, we should have X number of more planets, and by the time Plato finishes in the mid-2020s, we should have Y number more. And it still fits that trend, like it is still going. Eric Mamajek has some nice tweets about this. The distributions that I showed, kind of how the radii commonalities happen right now, we do think might change, especially if we get to a point of probing a different part of period space. So Kepler is only complete. It is only very likely to have detected planets that they have periods less than 100 days. And so right now, periods that are 100 days or longer, planets that are in orbit like the Earth, we actually don't know a ton about. And so as we move into different parts of parameter space, be it longer period planets, planets that are getting more or less energy and radiation from their stars, planets that are experiencing a high radiation because they're inactive stars, as opposed to IR radiation from quiet M dwarfs, it's very possible it could change. So there's a lot of qualifiers that go into things right now based on what we're sensitive to.
So maybe we shouldn't say that we're outliers.
Yeah, and so indeed, I think statistically, we can't actually say the solar system is a weird place yet. I don't remember the numbers, but there's a paper a year or two ago that basically says, because of how we observe and how long we've been observing for, we can't say that the solar system is weird. It kind of makes sense that we haven't seen ourselves yet. Because Jupiter takes 11 years to go around the sun. So you need to observe a system for at least 11 years to notice a planet like Jupiter. And this field only started exactly the exoplanet field as a whole is younger than I am, which is less impressive than when I said it as a second-year grad student. But still, it's been around for 20-something years. So
also, if the planet has a longer period, the chances that it'll line up to transit are that much less. So statistically, you're going to pick up far fewer of those. You have to wait longer, but you're still going to miss.
Yeah. And so this is why, for all of it, doing transit photometry is more efficient, and you can look at hundreds of thousands of stars at once. It's still not exceedingly sensitive to the vast majority of geometry alignments, and so things like radial velocity detections need to keep happening. We need to keep doing RV surveys that are not just transit follow-up, but are doing blind surveys focused on a number of stars that are some brightness and proximity criteria, and then monitor those to look for evidence of these long period giant planets. It's the only way we're going to find them right now. So, really?
In your predicted planets, I'm just curious, can you give a sense of the depth of the blockings kind of on average? In other words, if people are amateurs and thinking about looking for these transits, things like Kepler, those are on millimagnitudes, tiny, tiny signals. Very hard to do for amateur sets. I'm just curious what the range of these 1%ers.
Yeah, so the small planets are still going to be challenging just because that's how geometry works. Because TESS has this full frame image mode where it just takes a picture of whatever it's looking at every half hour, we are expecting a very large number, thousands or tens of thousands, of giant planet detections or even Saturn type things. And so those should be notably larger and I think would be very viable for doing ground-based follow-up. The other thing that will be, maybe this doesn't work well. So the other thing that TESS is going to do a lot of is because it only looks at most of the sky for a month, it's likely that we'll see a lot of signals that are just one transit, and then we won't be able to say here's the period of this thing. You'll only see it go by once. And so we're still trying to figure out basically how best to handle those and to get a better sense of like, is it a real planet? And if so, what kind of period is it on? And things like that. And so I know people have talked about ground-based resources for that, but without like, here's the transit window, I don't know exactly how you do it efficiently.
Wow. There's a lot of questions I want to try to make short, but I want to thank our speaker, Dr. Jennifer Burt. She might be available for a couple more as we enjoy some snacks. And thanks again to Maria. All right, I'm going to call an end of the meeting officially. So thank you all for coming. We had a great turnout. Appreciate it.
Thank you so much.